The focus of this video is running a simple or one-way ANOVA, calculating by hand using the formula. Simple analysis of variance, also known as one-way ANOVA, is used when we wish to compare the means of 3 or more groups. This is kind of like doing an independent samples t-test, but with more group means to compare. Simple analysis of variance requires that we conduct 2 steps. The first step of the ANOVA is called an omnibus test. In this step, we check to see if there are any group-by-group differences. The results of the omnibus test will give us a simple yes or no. Are there differences or not? But it will not tell us what those differences are. It simply says yes, there are some, or no, there aren't any. When the answer to the first step is yes, there are significant group-by-group differences, we then turn to our post hoc, or after-the-fact test. In the post hoc test, we look at which group-by-group differences were significant. So the first step asks, are there any significant differences? If the answer is yes, then we do the second step, and we ask which group-by-group differences were significant. If the answer to step 1 was no, we simply report that the group differences were not significant, and we give the means and SDs for part 2. So step 1, omnibus or overarching test. Step 2, post hoc or detailed after the fact tests. These 2 parts together are the necessary steps for completing a simple ANOVA. The first step is the omnibus test. The omnibus test uses the ANOVA F formula. So the symbol we use for the results of a one-way ANOVA is F. You'll actually see F used in other statistical tests as well. F is equal to the mean sum of squared deviations between groups divided by the mean sum of squared deviations within groups. So let's look at these 2 components, starting with the mean sum of squares between. The mean sum of squares between tells us how different groups are from one another. The second part is the mean sum of squares within. The within calculation focuses on how different individuals are from their groups. So if we put these 2 concepts together, what the ANOVA is actually asking is how much group versus group difference is there relative to how much person versus person difference is there. When an ANOVA is significant, it means that the differences from group to group are larger than the differences we see among individuals. Essentially what we're asking is, are group members more similar to each other than groups are to other groups? Let's use height to demonstrate what we mean. Say I have 3 groups of people, and I hypothesize that the mean height for group 1 is not the same as the mean height for group 2, which is not the same as the mean height for group 3. Then I would look at the actual heights of members of the 3 groups to see if my hypothesis is correct. Let's start by looking at differences within each group. You can see that in each group people are not the same height. Look at group 1. The heights of these persons are not equivalent. The same is true for group 2 and for group 3. So we see variation within each group. Let's examine group 1. I drew a line approximating the height of the shortest person and another one approximating the height of the tallest person in the group. This gives us a range of heights, so you can see that the persons in this group did vary around this little range from the shortest to the tallest person. I'll do the same thing for group 2. I've drawn a line across the top of the shortest person and across the top of the tallest person, so again we're seeing a little range here. Okay. Now when I look at individuals in group 2, they're not all the same height. There's a little bit of variation. The same thing was observed in group 1. Now we'll look at group 3. Again, we see this variation in group 3. So I can see that persons in each group are not all the same height. That's what's going on within each group. To do an ANOVA, we want to compare what's happening within each group to what's happening between each group. I've drawn a line showing the approximate heights of the purple group, and I've extended it across the other two groups. Thus, I'm looking at the range of heights in group 1 compared to the range of heights in group 2 and 3. Notice there's this distinction here. Group 2, their tallest person, is shorter than the low end range of group 1. So all the people in group 2 are shorter than the shortest person in group 1. Let's take a look at the same thing in group 3. The shortest person in group 3 is taller than the tallest person in group 1. So it appears that group 1 is taller in general than group 2 and shorter in general than group 3. I've repeated this by drawing a line from the group 2 variation across to groups 1 and 3. You can see clearly here that that green bar extending across all groups representing group 2 is below the ranges, the blue ranges of variation within group 1 and group 3. So everyone in group 2 appears to be shorter than the people in group 1 or group 3. I've repeated this process for group 3, and I can see that their range of heights are higher than all the people in group 1 and group 2. So though I'm seeing variation inside each group, represented by that little blue range that I drew for each group, I'm seeing gaps in the heights of those bars. That is, I'm seeing that the groups are more different when I compare each group to each other group than individuals are inside the groups. Another way of saying this is, though individuals varied in height, the way those groups varied did not cross. That means that the height ranges of group 1 and group 2 did not overlap. The height ranges of group 2 and group 3 did not overlap, and the height ranges of group 1 and group 3 did not overlap. So essentially what I'm seeing is that groups were more distinct from one another than persons were to other persons. To say it another way, the groups were clearly distinct even after you took into account how distinct individuals were inside each group. So that's what the omnibus test is asking about in ANOVA. Is there clear group by group differences after you assess individual versus individual differences within each group? Let's consider a new hypothesis. Let's hypothesize that people who exercise, meditate, or do neither will have different mean stress levels. Here we have 3 distinct groups: those who only exercise, those who only meditate, and those who do neither of these things. In our hypothesis here, we're saying that the mean stress score for those who exercise is not equal to the mean stress score of those who meditate, and or is not equal to the mean stress score of those who do neither of these things. So our hypothesis is that these 3 groups have quite distinct means. The null hypothesis, as you may recall, is always a statement against our hypothesis. So the null would state people who exercise, meditate, or do neither do not have different mean stress levels. In symbol format, we would be stating that the mean of the exercise group is equal to the mean of the meditate group, which is equal to the mean of the neither group. So here we have our 2 hypotheses. It's time to look at data. Suppose I asked people who exercised, meditated, or did neither how stressed they were on a scale from 0, not at all stressed, to 10, extremely stressed, and their scores were as follows. The persons who exercised had stress scores of 3, 4, 3, 5, 2, and 3. Those who meditated had stress scores of 4, 5, 5, 3, 4, and 2. And those who did neither of these things had stress scores of 6, 7, 5, 7, 8, 8. I want to take a moment here to point out that if a person exercised and meditated, then they could not be included in this particular study because you can't have crossover in your groups. The groups need to be 100% distinct, just like they would be in an independent samples t-test when we're using this simple version of ANOVA. There are other more complex methods you can do in ANOVA where the same group is tested multiple times. That's called a repeated measures ANOVA. but we're not focusing on that version in this video. To remind, our formula asks us to find the mean sum of squares between and then the mean sum of squares within so we can do some division. We'll start by looking at the mean sum of squares within because it's more similar to things that are done in the independent samples t-test and or when we calculate standard deviation or variance. The mean sum of squares within is actually its own little formula, which is total sum of squares within divided by degrees of freedom within. So we're going to do the sum of squares within each group first. Recall that sum of squares typically means the summation of deviations which have been squared. You see this in the standard deviation formula. So let's start by finding the sum of squares within group 1. I'm going to copy the data over on my scratch paper to make this a little easier for myself so I have space. The first step to finding the sum of squares is to calculate the mean for the group. Recall that the mean is calculated by finding the sum of raw scores divided by sample size. Using the formula, I find that the result is 3.33 continuous, so that's 3.33 out to infinity. So I'm going to use that as my mean, and I'll keep it to at least 4 decimal places so that when I'm doing my calculations, I won't have a ton of rounding error. So I'm going to subtract that mean from each raw score to find the individual deviations. I find that the deviations are negative 0.3 continuous, 0.6 continuous, negative 0.3 continuous, 1.6 continuous, negative 1.3 continuous, and negative 0.3 continuous. If I were to add all these up, they would sum to 0. So the next thing I need to do is square each of my deviations. I'm going to make sure that when I'm doing my squaring, I put brackets around my negative numbers so that it reminds me that the negatives are going to become positives once they are squared. Notice that my squared deviations all came out positive. I do have a little bit of rounding error in some of these because I was rounding to the 4th decimal place, but that's okay. So my last step here to find the sum of squared deviations for group 1 is to add. And I should get approximately 5.3334 here. If you had no rounding error, you might get 5.3333 if you rounded it to 4 decimal places. But we're okay here. We're burying any error out in that last place. So I'm going to write my final SSW for group 1 underneath their data so I can keep things organized. So I'm going to put that 5.3334 here. Pause here and try finding the SSW for the meditation group. Hit play when you're ready to check your answer. For group 2, I get a mean of 3.83 continuous, so I'm going to round that to 3.8333. I've subtracted that from each raw score to generate the deviation. Now I need to square each of those deviations to get the squared deviations. And when I sum those squared deviations, I get 6.8333. So my sum of squares within for group 2 is 6.8333. Now pause and calculate the SSW for the third group and hit play to check your work. The mean for the third group was 6.83 continuous, so I'm going to round to 6.8333. Next, I'll find the deviations by subtracting the mean from each raw score. Now that I have the deviations, I'll square each one. I get all positive numbers, of course, and I've got a little bit of rounding error in that last decimal place, but that's okay. And then we're going to add those to get the sum of squared within for group 3. When I do this, I get that the SSW for group 3 is equal to 6.8334. Now that last 4 would be a 3 if you didn't do any rounding in your earlier steps. We're going to allow a little tiny bit of rounding error way out in that 4th decimal place. Our formula calls for the overall SSW, so that means we're going to need to add the SSW for group 1 to group 2 to group 3. So my sum of squares within for all 3 groups together is 19.0000. Next up, we need to deal with the degrees of freedom within. Degrees of freedom within is calculated as total sample size minus the number of groups. The symbol we use for total sample size when there are multiple groups is capital N, and the symbol we use to stand for number of groups is lowercase k. This time we had 18 people because there were 6 people in 3 groups, So we're going to take 18 total people minus the number of groups they were constrained or split into, that's 3. So our degrees of freedom within is 15. Now we have the pieces we need to find the MSW. MSW is equal to sum of squares within, which was 19.0000, divided by degrees of freedom within, which was 15. So my MSW is equal to 1.266 continuous. So I'm going to put that to 4 decimal places. That's 1.2667. The MSW is meant to represent how different individuals were from their own groups on average. And we sum those individual SSWs to get the total person versus person variation happening within the groups in our whole big test. I'm going to fill that into my formula on the top since I've got the MSW completed. Now we're ready to move on to the MSB. The MSB is an estimate of how distinct groups are from other groups. So instead of comparing individuals to their group means, we're going to compare group means to something called a grand mean. The grand mean is calculated by treating all members of each subgroup or subsample as though they're part of one big group. So to find the grand mean, we use the exact same formula we would use to find individual group means, but we put all the people when we sum x. When I add every one of the raw scores together, I get a sum of x equal to 84. I'm going to divide it by my mega sample size, that's all groups treated as 1. I have 6 people in each group, so my total sample size is 18. So my grand mean in this situation is 4.6666 continuous, so I'm going to round that to 4.6667. So my grand mean, that is, when I treat all of these persons as though they're members of one big group, is 4.6667. We already found the mean for each individual group. To find the SSB, we do something similar to SSW, but we're looking at little group versus big group instead of person versus group. So let's look at the steps here. We would need to find the deviation of group versus grand. That means find the group mean and subtract from it the grand mean. We then are going to square those just like we always do when finding sum of squares. But we've got an extra step this time, which is multiply by n. The reason for this new step is because the group minus grand represents each person in the group, so each person needs to get weighed back into that estimate. Let's start by finding the SSB for group 1. The sample size is 6. The group mean is 3.3333. The grand mean is 4.6667, which we will square to get our answer. I start by doing my subtraction within parentheses, then I square that number in parentheses, and finally multiply by the sample size. And I get that the SSB for the first group is 10.6677. I have a little bit of rounding error out here at the end, so you might have a slightly different answer if you don't round at all, and that's okay. So I'll write my SSB over on the side so I don't lose track of it, and now I'll repeat those same steps for group 2. Pause here and find the SSB for group 2, then hit play to check your work. I find that the SSB for group 2 is 4.1676. Now pause and repeat the step to find the SSB for the third group, then hit play to check your work. Following these steps, I find the SSB for group 3 is equal to 28.1676, again with a little bit of rounding error. To get the total SSB for our ANOVA, I need to add the 3 individual SSBs. When I do this, I get 43.0029. Our MSB requires that we find SSB divided by DFB. Degrees of freedom between is equal to the number of groups minus 1. Therefore, the DFB in this scenario is equal to 3 minus 1, or 2. Therefore, our MSB is equal to 43.0029 divided by 2, which is 21.5015 if we round it to 4 decimal places. Now again, I want to point out that this has got some rounding error here at the end, but that's okay. I can now put my MSB in the top part of the formula, and I'm ready to solve for f. F is equal to MSB divided by MSW. So in this case, that's 21.5015 divided by 1.2667, which gives me 16.9744. So the result of our omnibus test, part 1 of an ANOVA, is 16.9744. So our next question is whether our omnibus result of 16.9744 is significant. To know this, we have to look at a critical values table for ANOVA, also known as the critical values of F. Here's an example of a critical values table for ANOVA. We need to know the degrees of freedom between groups and the degrees of freedom within groups to find the critical value for any individual ANOVA. The critical values between move across the top of our sheet, whereas the critical values within move horizontally along the side. We had 15 degrees of freedom within because it was total sample size minus 3, and 2 degrees of freedom between because it was number of groups minus 1. So our critical value is going to be 3.68. Now notice there are two critical values here, 3.68 and 6.36. We use the one in bold because that equates to a 5% chance of a type 1 error. If we're using a 1% chance of a type 1 error, we'd use the bottom number. But because that's not typical in the behavioral sciences, we'll be using that bold number in top, the smaller number, 3.68. Our obtained value was 16.9744, and our critical value was 3.68. If the obtained value is greater in absolute value than the critical value, the result is significant. Another way of saying this is that if your obtained value is farther from 0 than the critical value, the result is significant. So let's take a look at what we have here. Our obtained value is much larger in absolute value than the critical value, so our result is statistically significant. So I can summarize that the means of the three groups were significantly different, and then I'm going to use that APA format, where I give the symbol, and then I put the degrees of freedom in parentheses. For the ANOVA, we put the degrees of freedom between, followed by the degrees of freedom within. Then we put our obtained value rounded to the hundredths place, which is 16.97. And when the result is significant, we write p less than 0.05. The next thing to do after the omnibus test is to run the post hoc test so we can report those. Thankfully, we typically don't do these by hand. We typically use computer software to compare the means of each group so that we can find out which group was different from which other group. Because our result so far only tells us that at least one group was different from at least one other group, but the post hocs let us dig in further. So we're going to take a look at how that's done using SPSS software. SPSS is a statistical software package that's commonly used by behavioral scientists. We can use this to calculate both descriptive and inferential statistics. Keep in mind that there are other kinds of software available out there, but I'll be focusing on SPSS. If you need to run analyses from start to finish using SPSS, you'll first want to open your software and set up information about your variables. To establish information about your variables, you need to click on Variable View on the bottom tab. This allows us to put information in about the variables themselves, what we want to call them or their names, whether they are quantitative or qualitative. We typically write numeric if they are quantitative. And then we give a label. What do we want to call that variable if we create a graph? Typically here we just call it the exact same thing that we named the variable. For your quantitative variable, in this case it would be stress, there's not really anything else we need to put here, other than we'll switch the measure type over here to be scale. Here it's showing as nominal because things are being set up. Your group variable is qualitative, so for this one, we need to put what the values will be equal to. What this means is that we assign each group a number to represent its name. In order for me to assign those names, I would click into that value cell that's highlighted in yellow, and a window like this would pop open, where I'd put the value I'm using and then the label that it stands for, like the exercise group. Then I would hit Add to move that label into the box. Once I've put in the label for each of the values, I click OK, and it'll enter it into my values section. Once you've done that, you're ready to enter your raw scores. To enter our raw scores, we need to click on Data View at the bottom, and that'll bring us to the page where data can be entered. Now I'm on the data slide where I can put my data. You'll notice that the names of the two variables I created appear at the top of the first two columns. These other ones just say var because they're waiting in case you want to add other variables. But because we only have two, only two are going to appear there. And then I'll fill the data in underneath those titles. Notice that on the bottom corner it shows in gold that we're on the data view section of SPSS. It looks kind of like an Excel spreadsheet, though Excel is typically green and SPSS is typically blue. Recall that just a moment ago, we decided that the exercise group would be called Group 1, so you'll see their scores. And then next to their group label of 1, you see the stress scores for the persons that were in that group, which were 3, 4, 3, 5, 2, and 3. Then we have the stress scores for the second group. There were 6 people whose stress scores were 4, 5, 5, 3, 4, and 2. And then we had 6 people in group 3, which were the folks who neither exercised nor meditated. And they had stress scores of 6, 7, 5, 7, 8, and 8. So notice here that the group label goes in the first column, and the stress scores that correspond to those individuals go in the second column. Now we're ready to run our test. To run any test, we go up to Analyze, and we click that, our options window will pull down, showing us the kinds of tests we can do. We were interested in comparing the means of the group, so when I click on that, it'll open a secondary window to let me choose between t-test or the ANOVA. We want the ANOVA, so I'm going to click Analyze, Compare Means, then One-Way ANOVA. Once I do that, the One-Way ANOVA box will open. This is where I'm going to set up what it is I wish to test. I'll select my grouping variable, which is called group conveniently, and put it down here where it says factor. Factor is another fancy way of saying group, or the way you're separating groups. Then I'm going to put the test variable, the dependent variable, which is quantitative, in this case stress, into the dependence box. Then I would click on post hoc so I can dictate that I do want to know those post hoc analyses, because what I'm putting in these first two spaces is going to do the omnibus, and I have to separately ask for the post hoc results. The most commonly used post hoc is going to be Tukey's, so we're just going to click that here. Now these other ones are used in various situations, but Tukey's is a commonly used one when variances between groups are similar. If variances are not similar, which is not going to be something we'll review in this video, then we use one of these other versions of the post hoc test. Notice that it automatically filled in at the bottom that the significance level will be set at p less than 0.05. That's the most commonly used one in the behavioral sciences. This translates to calling the result significant if there's less than a 5% chance of a type 1 error. So we'll leave that at that preset because that's what we typically use. Then we'll click on Continue to accept the post hoc, and then OK to run the analysis. Before we look at the results, let's stop here to note something about the actual process of conducting research. Many statistical tests, including ANOVA and the independent samples t-tests, have assumptions that analysts check before they can calculate their results. An assumption is something that needs to be true for the statistical process or the formula to function well. The independent samples t-test and the ANOVA both have the assumption that the variances in group 1 and group 2 are somewhat similar. Notice that the ANOVA test is an analysis of variance. This means that variation is important to this test, and therefore we need to check an assumption about it. It's presumed that the variances of all groups in an independent samples t-test or an ANOVA are approximately equal. There's a test called the Levene's test for homogeneity of variances that checks this for us. To be homogeneous means to be similar. So what the Levene's test is assessing is whether the variances are similar or the same in the different groups. The Levene's test checks to see if there is a problematic difference in our variances. That means it's checking to see if there's a problem due to our variances being too dissimilar. For these reasons, we want Levene's to be non-significant because significance here means there's a problem with our data. So we look at the Levene statistic here. We want this number to be very small, close to 0, and it is. It's 0.06 if we round to the hundredths place. And we want the significance level to be greater than 0.05. And the sig level it's 0.94. So this is saying we can be 94% confident there's no issue here if we move forward. And again, we just want this to not be significant. We want that p-value to be greater than 0.05, indicating there's no problem and we can move forward. Since we've checked our assumption and everything was okay there, we can look at the omnibus results from SPSS. SPSS will give you your output in a window like this. This is sometimes known as a source table. The source table shows us a few important things, such as our between groups sum of squares, degrees of freedom, and mean sum of squares, and our within groups sum of squares, degrees of freedom, and mean sum of squares. It also shows us the F value. And then finally, it shows us the significance, whether or not our omnibus test had a significant result. Compare these results to what we found when we calculated by hand. They're pretty close. We just have a little bit of rounding error in some of our numbers, but that's not too big of a problem as long as our F value turns out to be as expected. This is telling me that my F value with 2,15 degrees of freedom is equal to 16.97, and that is significant at p less than 0.05 because we set our sig value to be less than 0.05. This is exactly what we found when we calculated this by hand, but the computer can do this in just a few seconds. Once we've established that the omnibus test is significant, we're ready to look at our post hoc results. Now, these can look a little confusing when we first look at them. We're going to start by looking at the multiple comparisons table, the one that looks the most confusing when you're looking at these output. There's a lot of information in this table, but we can simplify it by focusing in on what we need. First, we have 3 group-by-group comparisons we want to check. I want to compare the stress results of those who exercised compared to those who meditated, those who exercised compared to those who didn't do anything, and those who meditated versus doing neither of these things. Let's start by looking for the results of those who exercised versus those who meditated. The group who exercised compared to who meditated have a significance level of 0.727. That means that the result, the difference between these two, is not significant because that p-value here is greater than 0.05. The second post hoc we want to look at compares those who exercised to those who did neither. I can compare those who exercised to those who did neither, and I see that their significance level is 0.000. That is a significant result because we want that p to be less than 0.05. So this is significant, p less than 0.05. So now we've had one non-significant result and one significant result. Now on to our third and final post hoc comparison. That's those who meditated compared to those who didn't do either thing. I'm going to look at their data, look for their p-value, and I see that their p-value is less than 0.05. So the meditation mean compared to the neither mean is significant at p less than 0.05. So my omnibus told me that I would have at least one significant group-by-group difference. My comparison of the first two groups showed me a non-significant result, but comparing the other two groups showed significant results. So my pattern here is that those who did neither thing are different than those who did either thing. But my persons who exercised versus meditated, my two groups of folks who did something, were not significantly different. Let's take a look at the means of those groups to better understand this. The mean and standard deviation for those who exercised was 3.33 and 1.03 respectively. For those who meditated, the mean was slightly higher at 3.83, with a standard deviation that's slightly higher at 1.17 if we round to the hundredths place. But our group who did neither had a much higher mean of 6.83 with a standard deviation of 1.17. So when I'm looking at these scores down here, the means, it's pretty clear to me that groups 1 and 2, those who exercised and meditated, look similar, but that our third group, those who did neither, are looking quite a bit distinct. Their mean is much higher compared to the means of the other two groups, which were rather similar. And my results here bear that out. I'm seeing that the first two groups, exercise and meditation, were not significantly different, where the other two comparisons did have significant differences. Let's take a look at a graph to help us visualize this similarity and dissimilarity. Here I've created a bar graph with the stress scores for the exercise, meditation, and neither group. Notice here that the means for stress of folks who either exercised or meditated are pretty similar, but the mean for the persons who did neither is much higher on the graph. The appearance is that these two are close, but that this one here, the third group, is a lot higher than the second group or the first group. So our results are telling us that the difference we're seeing from group 1 to group 2 is not significant. It's too similar, and if we look at those bars, they look a lot alike. But that the third group mean is really dissimilar from the other two, much higher than their means. Let's visualize this another way by drawing the normal curves that represent these three groups on a number line. The means for the three groups appear on my bars, but I'm going to need those standard deviations to help me sketch my normal curves. We saw in the SPSS output that the standard deviations were 1.03, 1.17, and 1.17 for the exercise, meditation, and neither group, respectively. I'll use what I know about sketching normal curves to draw each of these three graphs, starting with the exercise group, which I'll represent in pink, followed by the meditation group, which I represent with green, and last will be my neither group in gold. Once I've sketched all three of my normal curves for these data, you can see once again that that gold group looks really distinct from the other two groups, and that those other two groups, those who exercised and meditated, are looking really similar. And there's not a lot of crossover between those two groups. It's only the tails of my graphs that appear to be crossing. The bulk of my graphs are in different locations relative to one another. So there's not a lot of crossover in where scores tended to be. When we say that group 3 is significantly different from the other two groups, this is what we're talking about. And when we say that groups 1 and 2 are not significantly different, we're referring to the fact that those graphs look really similar in their location on the number line. So this brings us to our last step for any inferential test. We must write our results in APA format. APA format is a pretty strict format that dictates the way we write up our results and the place to which we will round specific numbers. Any computed number that can exist other than an integer or whole number, that means anything with a meaningful decimal place, should be rounded to the hundredths place. Anything that can only exist in a whole number, such as the sample size, we can show rounded to the whole number. But means, standard deviations, F and P must be shown to the hundredths place. The first sentence for an APA formatted write-up for an inferential test always states the name of the test that was used and what the hypothesis was. So I'll start by saying a one-way ANOVA was used to test the hypothesis that those who exercised, meditated, or did neither would have different average stress scores. Then we state the results of the omnibus test and say whether those were significant. So I've written the mean stress scores of the three groups were significantly different. Notice I've got that word significant. We either need to say whether it was or was not here. And then I'm going to present the important APA evidence at the end. giving the symbol for the test, which was F, degrees of freedom represented in parentheses, then the obtained value from the formula, and then if our result is significant, we write p less than 0.05. If our result was not significant, we would have written p greater than 0.05. And then finally, we provide the details that we got from the post hocs. This must include giving the mean and standard deviation for each group rounded to the hundredths place and stating whether the group-by-group comparisons were significant. I'm going to use two sentences to break up my results part so that you don't get one overwhelming sentence of post hoc results. So I'll start by saying, specifically, those who exercised give their mean and standard deviation to the hundredths, and those who meditated give their mean and standard deviation to the hundredths had significantly lower mean stress than those who did neither, and then give that group's mean and standard deviation rounded to the hundredths. Because I'm noting that a difference was significant, I need to give that p-value of p less than 0.05. I don't need to repeat the omnibus result of that f of 2, 15 equals 16.97 here, because that would be redundant. We already know that above. All we need now is the post hoc means, SDs, and p-values. I've got one sentence to go because I need to tell you whether there was a difference between those who exercised and those who meditated. So for my final sentence, I will say, however, those who exercised and those who meditated did not have significantly different levels of mean stress. And I'm going to put p greater than 0.05 because that means the result is not significant. You might notice here that I didn't give the means and SDs for the group in this sentence. I don't need to because I already gave all the group means and SDs in the previous sentence. So to provide them here would be to be redundant. And we don't want redundancy, we want clarity and simplicity. So take a look at how action-packed our final paragraph is. We're getting a lot of information here. We know the test used, the hypothesis, whether the omnibus was significant, and then we know each of the group-by-group comparisons and each group's mean and standard deviation. This should be the template you use to write a results paragraph anytime you do a one-way ANOVA.